Hi everyone. Welcome. Welcome to Quiet This Journey. Tonight, we're going to talk about something very old. Something that happened long before any of us were here. Long before cities or roads, or even the first trees. We're going to talk about ice ages. And how, very slowly, very gently, they begin. Ice ages are not sudden things. They don't arrive quickly. They come in the way that seasons change. Almost without you noticing, 1 degree at a time, one quiet year folding into the next. And that softness, that patience, that slow unfolding, makes it a very lovely thing to think about as you drift towards sleep. So take a breath, let your shoulders settle, and let's begin. Slowly, together. The Earth is a very old place, about 4.5 billion years old, to be precise. And in all that time, the planet has gone through long periods of warmth and long periods of cold. These cold periods, the ones where great sheets of ice spread across the land, are called ice ages. But here's something quietly wonderful to consider. We are actually living inside an ice age right now. It's called the Quaternary Ice Age, and it began about 2.5 million years ago. The reason it doesn't feel like an ice age is because we're currently in what's known as an interglacial period, a warm phase within the larger cold era. The ice hasn't gone away entirely. It's still sitting quietly at the poles, waiting, just thinner and more withdrawn than it was before. So in a soft sense, the ice is still here. It never truly left. Within a single ice age, there are pulses of cold and warmth that come and go like a very slow breath. The colder phases are called glacial periods, and the warmer ones are called interglacials. Right now, we are in an interglacial called the Holocene, which began about 11,700 years ago. Before the Holocene, glaciers stretched across much of North America and Europe, burying landscapes under ice that was sometimes 2 or even 3 kilometers thick. And before that warm phase began, those same landscapes were quiet and frozen for tens of thousands of years. The ice moved slowly, only a few meters per year in many places, grinding rocks into fine powder and carving out the valleys we now call home. It is a kind of slow sculpture, the land shaped by patience, by cold, by time. Ice ages are not random events. They follow patterns. Quiet, rhythmic patterns that are tied to the way the Earth moves through space. These patterns were first described mathematically by a Serbian scientist named Milutin Milankovic in the early 20th century. He spent years working out the mathematics of Earth's orbit and tilt, calculating by hand how the amount of sunlight reaching different parts of the planet changes over thousands of years. He found that the Earth wobbles and tilts and stretches its orbit in very slow cycles, and that these cycles, layered on top of each other, create the rhythm of ice ages. His work was not widely accepted at first. For decades it sat quietly, waiting. But eventually, the ocean sediments confirmed what he had calculated, and today his name is given to the very cycles he described. There is something peaceful in that, a patient idea waiting to be understood. Now, as we continue, let's think about the shape of the Earth's path through space. The Earth does not travel around the sun in a perfect circle. It travels in an ellipse, a slightly oval shape. And over a cycle of about 100,000 years, that oval shape changes. Sometimes it is more circular, and sometimes it is more stretched. This is called eccentricity. When the orbit is more stretched, the difference between the Earth's closest and farthest point from the sun becomes larger. This means that the amount of sunlight reaching Earth changes more dramatically across the year. When the orbit is nearly circular, the seasonal differences in sunlight are gentler, more even. Right now, the Earth's orbit is fairly close to circular, meaning the difference between our nearest and farthest point from the sun is relatively small. This gentle, slow stretching and relaxing of the orbit takes about 100,000 years to complete one full cycle, like a very slow, very deep breath of the solar system. As the Earth travels around the Sun, it also spins on its own axis. And that axis is tilted, not perfectly upright, but leaning at an angle. Right now, that tilt is about 23.5 degrees. But the tilt itself changes slowly over time, varying between about 22 degrees and 24.5 degrees over a cycle of roughly 41,000 years. This is called obliquity. When the tilt is greater, the seasons become more extreme. Summers are warmer, winters are colder. When the tilt is smaller, the seasons are more moderate, cooler summers and slightly milder winters. Cooler summers are actually very important for ice ages, because they allow snow and ice from winter to survive through the summer without melting. The tilt of the Earth, changing so slowly that no human life could perceive it directly, quietly shapes whether ice sheets grow or shrink across the centuries. Gently moving forward, let's rest on another quiet idea. There is a third way the Earth's motion changes, and it is perhaps the most graceful to imagine. As the Earth spins, it wobbles very slightly, the way a spinning top wobbles as it slows down. This wobble is called precession. Over a cycle of about 26,000 years, the direction that Earth's axis points slowly traces a circle in the sky. Right now, our North Pole points toward a star called Polaris. But about 13,000 years ago, it pointed toward a star called Vega instead. This wobble changes which season falls at which point in Earth's orbit, meaning it changes whether the northern hemisphere's winter happens when the Earth is closest to the Sun or farthest from it. This matters enormously for climate. Precession quietly shifts the timing of the seasons relative to the orbit, nudging the planet, very gently, toward cold or toward warmth over tens of thousands of years. When scientists talk about Milankovitch cycles, they mean all three of these motions layered together: the stretching of the orbit, the tilting of the axis, and the wobble of the spin. Each one operates on a different timescale, and they overlap and interfere with each other in complex ways. Sometimes they line up so that they all push the climate in the same direction, toward cold. When that happens, conditions are right for an ice age to begin. But even then, the process is slow. It takes thousands of years for ice to build up, for the oceans to cool, for the atmosphere to respond. There is no single moment when an ice age begins. Instead, it arrives the way sleep arrives, gradually, almost without notice, one quiet moment giving way to the next. The world simply cools, softly, over a very long time. Let's take a quiet moment to think about sunlight. Sunlight is the engine of Earth's climate. Everything, the warmth of the oceans, the movement of the winds, the growth of forests, ultimately traces back to sunlight arriving from the sun, 93 million miles away. The total amount of sunlight reaching Earth doesn't change very much over time. But where that sunlight falls, and when, and at what angle, those things do change. And it turns out that the distribution of sunlight matters enormously. A small shift in how much sunlight falls on the high northern latitudes in summer, places like Canada, Siberia, and Scandinavia, can be enough to tip the balance between ice melting and ice surviving. This is because the large land masses of the northern hemisphere are where the big ice sheets form. If summers in those regions become just a little cooler, just enough so that last winter's snow doesn't entirely melt, the ice begins to accumulate. Year by year, quietly, the ice deepens. There's a concept in climate science called the ice albedo feedback, and it is one of the gentlest, most elegant ideas in all of Earth science. Albedo is just the word for how much sunlight a surface reflects. Fresh snow has very high albedo. It reflects back about 90% of the sunlight that hits it. Dark ocean water has very low albedo. it absorbs most of the sunlight that falls on it. So here is the gentle loop. When ice forms and spreads, it reflects more sunlight back into space, which makes the Earth cooler, which allows more ice to form, which reflects more sunlight, which makes the Earth cooler still. It is a feedback loop that amplifies itself quietly, like a whispered conversation that grows slightly louder with each repetition. Once ice begins to grow, this feedback helps it grow further, slowly, steadily, over thousands of years. Now, as we continue, let's rest on the thought of ice spreading across a quiet land. Imagine standing at the edge of a glacier. Not a dramatic scene, just a quiet afternoon, somewhere in a northern landscape. The air is very still. The ice in front of you is gray-white, streaked with dirt and dust picked up from the ground. It doesn't look like it's moving. And in human time, it isn't not really. Glaciers typically move a few centimeters to a few meters per day, depending on conditions. Some move faster, some slower. But the key thing is that they are always moving, always flowing, under their own enormous weight, downhill and outward. A glacier is not frozen still. It is flowing, very slowly, like the thickest possible river. And when conditions cool enough, and enough snow accumulates year after year, these slow rivers of ice begin to extend further, reaching across valleys, covering hills, filling in the spaces between mountains with quiet, creeping white. Snow is not just frozen water. It is a crystal structure, one of the most varied and intricate natural structures in the world. Each snowflake forms around a tiny particle of dust or pollen in the atmosphere. Water vapor freezes onto this particle in a hexagonal pattern because of the geometry of the water molecule itself. As the crystal falls through different layers of air with different temperatures and humidity levels, it grows into one of an essentially infinite number of shapes. No two snowflakes follow exactly the same path through the atmosphere, and so no two snowflakes are exactly alike. But when snow accumulates on the ground over many years, the individual crystals slowly compress. The beautiful lacy structures collapse. The air is squeezed out, and eventually, over decades and centuries, the snow transforms into the dense, bluish ice of a glacier. Beauty, slowly, quietly, becoming something ancient and enormous. The color of glacier ice is something people sometimes find surprising. Deep, old glacier ice is often a very pale, delicate blue. This happens because of the way ice absorbs light. Ice absorbs slightly more of the red end of the light spectrum and reflects the blue end. The deeper and denser the ice, the more this effect becomes visible. In the very oldest, most compressed parts of a glacier, ice that might be hundreds of thousands of years old, the blue can be quite vivid. It is one of the quietest and most beautiful colors in nature, a blue that took 10,000 years to appear. And within that ancient ice, there are tiny bubbles of air from the atmosphere as it existed when that snow first fell. Scientists can drill into glaciers and extract these air bubbles, reading the ancient atmosphere the way you might read a very old, very slow diary. Gently moving forward, toward the idea of the ocean and how it holds memory. The ocean is a vast storage system for heat. It absorbs sunlight during warm periods and releases that heat slowly over time. Because the ocean has such enormous thermal mass, because it takes so much energy to change the temperature of all that water, it acts as a kind of buffer or dampener for the climate. It slows down changes. When the atmosphere begins to cool, the ocean resists, holding on to its warmth for centuries. And when conditions warm again, the ocean slowly releases that stored cold back into the atmosphere. This is one reason why ice ages build so gradually. The ocean is always moderating, always smoothing out the changes, always responding slowly to what the atmosphere and the sun are doing. The deep ocean, in particular, is extraordinarily slow to change. Temperatures at the seafloor may take thousands of years to fully respond to changes at the surface. The deep ocean is one of the most stable environments on Earth. At depths of 2 or 3 kilometers, the temperature stays near freezing year-round, regardless of what is happening at the surface. The water there is very still, very cold, very dark. It moves in very slow currents, called thermohaline circulation, or sometimes the ocean conveyor belt, that can take 1,000 years or more to complete a full circuit of the globe. This deep circulation is driven by differences in water temperature and salinity. Cold, salty water is denser than warm, fresh water, so it sinks. In the North Atlantic, surface water cools and sinks, driving a current that pulls warm water up from the tropics to replace it. This current brings warmth to northwestern Europe and plays a crucial role in moderating the climate of the northern hemisphere. When ice ages begin, this circulation can slow or shift, changing the distribution of heat around the planet. There is no need to rush. The continents are not fixed in place. Over millions of years, they move, drifting across the surface of the Earth on great plates of rock that float on the slowly convecting mantle below. This process is called plate tectonics, and it moves the continents at about the same rate that your fingernails grow, a few centimeters per year. But over millions of years, this adds up. Continents have been in very different positions in the deep past. And the arrangement of the continents matters enormously for climate. Land masses near the poles can accumulate ice. Continents blocking ocean currents can change how heat is distributed around the world. Antarctica drifting to the South Pole, about 34 million years ago, allowed a circular current to develop around it, the Antarctic Circumpolar Current, which isolated Antarctica from warm water and allowed permanent ice to form there. The stage for ice ages is partly set by where the continents happen to be. Mountain ranges also play a quiet but important role in how ice ages unfold. When mountains are pushed up by tectonic collisions, they change the way air moves across the land. Air is forced upward over mountain ranges, cooling as it rises, losing its moisture as snow or rain on the windward side, and arriving dry and warm on the leeward side. This creates distinct wet and dry regions. The Himalayas, which formed when the Indian subcontinent collided with Asia about 50 million years ago, dramatically altered the climate of Asia by creating the monsoon system and changing wind patterns across the entire hemisphere. Mountains also experience more snowfall than lower ground, which means high mountain ranges can develop their own local glaciers, called alpine glaciers, that are separate from the great continental ice sheets. Mountains, rising slowly from tectonic forces, quietly reshape the flow of air and water across the world. Let's take a quiet moment to think about rocks and what they remember. Rocks are perhaps the most patient record keepers on Earth. Different types of rock form under different conditions, and by reading the rocks, scientists can reconstruct what the climate was like millions or even billions of years ago. Certain types of sedimentary rock, called tillites, form when glaciers deposit their load of ground-up material. Finding ancient tillite layers tells scientists that glaciers were present in that place at that time. Striations, long scratches in bedrock, are made by rocks embedded in the base of a glacier being dragged across the surface. These scratches survive for millions of years, pointing in the direction the ancient ice moved. The rocks of the Canadian Shield, the Scandinavian bedrock, and the floors of ancient valleys all carry these quiet marks of past glaciation. Scratches made in silence, preserved in stillness, waiting for someone to come along and read them. One of the most extraordinary examples of ancient glaciation recorded in rock is called Snowball Earth. About 700 million years ago, long before any complex life existed on land, there is evidence that the entire planet was covered in ice, from pole to equator. The oceans may have been frozen to a depth of hundreds of meters. The evidence for this comes from glacial deposits found in rocks that, at the time they formed, were at tropical latitudes. The idea of a completely frozen Earth is difficult to imagine, a world of white and silence, with no open water anywhere. How the Earth escaped from this frozen state is a fascinating question. Volcanic eruptions continued releasing carbon dioxide into the atmosphere, and over millions of years, with no rain to wash it away, CO2 built up until the greenhouse effect became strong enough to melt the ice. The planet slowly, quietly warmed again. Carbon dioxide is a very small part of Earth's atmosphere, currently about 420 parts per million, or roughly 0.042%. And yet this tiny fraction plays an enormous role in the planet's temperature. Carbon dioxide is a greenhouse gas, meaning it absorbs and re-emits infrared radiation, heat, that would otherwise escape into space. Without any greenhouse gases, the average temperature of Earth's surface would be about -18 degrees Celsius, well below freezing. With the greenhouse gases we have, the average is about 15 degrees Celsius, warm enough for liquid water, for life, for all the gentle complexity of the world. Changes in CO2 levels, even small ones, ripple through the climate system over centuries and millennia. During past ice ages, CO2 levels were lower, around 180 parts per million. During warm interglacials, they rose to about 280. These quiet fluctuations track the rhythm of the ice. Gently moving forward, let's think about how CO2 moves through the world. Carbon dioxide is constantly moving between the atmosphere, the oceans, and the living world. Plants absorb CO2 during photosynthesis, locking the carbon into leaves and wood and roots. When plants die and decompose, that carbon is released again. The ocean absorbs enormous amounts of CO2 from the atmosphere. Cold water dissolves CO2 more readily than warm water. During ice ages, with cooler oceans and less biological activity, more CO2 was drawn out of the atmosphere and stored in the deep ocean. This further cooled the planet, amplifying the glaciation in another gentle feedback loop. When the ice eventually retreated and the oceans warmed, CO2 was released back into the atmosphere, helping to warm the planet further. Carbon dioxide, moving silently through air and water and living things, is one of the quiet threads that ties the whole climate system together. And we can take a moment to notice how still everything feels. Ice cores are one of the most remarkable tools scientists have for understanding past climates. By drilling deep into the ice sheets of Greenland and Antarctica, researchers can extract cylinders of ice that were laid down layer by layer over hundreds of thousands of years. Each layer is a year of snow, and within each layer are tiny bubbles of ancient air, samples of the atmosphere from that year. Scientists can measure the CO2, methane, and other gases in those bubbles, effectively reading the composition of the atmosphere going back 800,000 years. In Antarctica, the deepest ice cores come from a place called Dome Sea, where ice has accumulated slowly and evenly for an extraordinarily long time. The ice from 800,000 years ago is compressed into layers near the bottom of the core, each one thinner than a sheet of paper, but still intact, still carrying its ancient air. Ice cores also preserve isotopic signatures that tell scientists about past temperatures. Water molecules contain either ordinary hydrogen or a slightly heavier version called deuterium. Cold water preferentially incorporates less deuterium, while warm water incorporates more. By measuring the ratio of these isotopes in ancient ice, scientists can estimate the temperature at the time the snow fell. This technique, called oxygen or hydrogen isotope analysis, has allowed researchers to reconstruct a detailed temperature record going back hundreds of thousands of years. The record shows a clear, rhythmic pattern, long periods of gradual cooling punctuated by relatively sharp warmings, that matches almost perfectly with the Milankovitch cycles. The ice remembers every temperature, every season, every quiet shift in the climate across 800 millennia. It holds all of this in silence, deep beneath the surface. Within ice cores, there are also layers of volcanic ash. When a major volcano erupts somewhere in the world, the ash and sulfur particles it ejects into the upper atmosphere can circle the globe and eventually settle onto the ice. These layers show up as thin, sometimes barely visible bands in the core. They act as time markers. If scientists can identify which eruption produced a particular ash layer, they can pin down that part of the ice record to a specific date. Some volcanic layers and ice cores come from eruptions that are well documented in history, like the eruption of Krakatoa in 1883, or the Tambora eruption in 1815, which caused what was called the Year Without a Summer. Others come from eruptions so ancient that they have left no other record anywhere. The ice quietly cataloged them all, undisturbed, for centuries. Now, as we continue, let's gently move to the idea of what ice feels like to the land. When a glacier moves across the land, it doesn't just sit there. It works. The immense weight of the ice presses down on the bedrock below, and as it moves, it grinds and scrapes and plucks rocks from the surface. Rocks become embedded in the base of the glacier and are dragged along, scoring long grooves in the bedrock, those striations we mentioned earlier. Boulders that are too large for rivers to carry can be picked up and transported enormous distances by glaciers. When the ice melts, these boulders are deposited far from where they originated, sometimes hundreds of kilometers away, sitting alone on landscapes that have no matching rock type nearby. These are called erratics, and they were some of the first evidence that scientists used to recognize that glaciers had once been far larger than they are today. There is something quietly wonderful about a rock that has traveled so far, carried so gently, left so far from home. The weight of an ice sheet is almost beyond imagining. The ice sheet that covered most of Canada during the last glacial maximum, about 20,000 years ago, was so heavy that it actually depressed the bedrock beneath it by hundreds of meters. The land sank under the weight of all that ice, the way a mattress sinks under the weight of someone lying on it. And when the ice eventually melted, about 10 to 15,000 years ago, the land began to slowly rise back up, a process that is still continuing today. This process is called glacial isostatic adjustment, or post-glacial rebound. Parts of Scandinavia and Canada are still rising by several millimeters per year. Even now, still recovering from ice that melted thousands of years ago. The land has a very long memory. It holds the impression of the ice long after the ice itself has gone. The Great Lakes of North America, Superior, Michigan, Huron, Erie, and Ontario are a direct gift of the last ice age. They were carved out by glaciers moving across the landscape, scooping out vast depressions in the bedrock, then filled with meltwater as the ice retreated. The basins were deepened by the repeated advance and retreat of ice over hundreds of thousands of years. Lake Superior, the largest freshwater lake in the world by surface area, sits in a basin that was scoured by ice to a depth of nearly 400 meters in some places. The gentle, quiet shores of these lakes, the morning mist, the cold, clear water, the rocky outcrops worn smooth, all carry the memory of the ice that made them. Every lake, every valley, every drumlin and esker in the glaciated landscape is a soft echo of the great ice that once lay there. Slowly, gently, the landscape carries the memory of cold. A drumlin is a smooth, elongated hill made of glacial till, the mixture of sand, gravel, and rock that glaciers deposit. Drumlins form beneath moving glaciers, shaped by the flow of ice over loose sediment. They are usually oval or tear-shaped, with the steeper end facing the direction from which the glacier came. In parts of Ireland, Canada, and the northern United States, drumlins cover the landscape in great swarms, thousands of them, all oriented in the same direction, like gentle waves frozen in stone. From the air, a drumlin field looks like the back of a sleeping giant. From the ground, the hills are soft and rounded, covered in grass, quiet and unhurried. They don't announce themselves as monuments to the Ice Age. They simply sit there, curved and calm, shaped by a process that ended thousands of years before any human eyes saw them. An esker is another gift of the retreating ice, a long, winding ridge of sand and gravel that was deposited by a meltwater river flowing through a tunnel in or under the glacier. When the ice melted, the river channel collapsed, leaving behind a ridge that winds across the landscape like a frozen river. Some eskers run for hundreds of kilometers, curving and bending through the terrain. They are often narrow, just a few meters wide at the top, and surprisingly high, sometimes 10 or 20 meters tall. Walking along an esker is a strange and quiet experience. You are standing on a river of ancient meltwater, formed in a dark tunnel beneath a glacier that has been gone for 10,000 years. The material under your feet flowed there in darkness, deposited grain by grain as the ice above slowly wasted away. There is no need to rush. The atmosphere is a very thin layer. If the Earth were the size of an apple, the atmosphere would be no thicker than the apple's skin. And yet within this thin skin, all of the weather, all of the climate, all of the gentle movement of air and moisture that makes the surface habitable happens. The atmosphere is mostly nitrogen, about 78%, followed by oxygen at about 21%. Everything else, argon, carbon dioxide, water vapor, methane, and all the other trace gases, makes up just the remaining 1%. And yet that 1%, especially the greenhouse gases within it, governs the planet's temperature in profound ways. The atmosphere is both very thin and very powerful. It is a delicate film that keeps the surface warm, distributes the sun's energy, and moderates the extremes of space that would otherwise make the surface uninhabitable. Methane is another greenhouse gas that plays a role in Ice Age cycles. It is much more potent than CO2 as a greenhouse gas, molecule for molecule. It traps far more heat, but there is much less of it in the atmosphere. Methane is produced by wetlands, by the decomposition of organic matter in low-oxygen environments, and by various biological processes. During warm interglacial periods, the expansion of tropical wetlands and the thawing of permafrost releases more methane into the atmosphere. During glacial periods, as wetlands shrink and permafrost expands, methane levels drop. Ice cores show that methane levels have tracked the Ice Age cycles closely, rising during warm periods, falling during cold ones. Like CO2, methane's fluctuations amplify the initial climate signals, quietly pushing the climate further in whichever direction it is already heading. Let's take a quiet moment to think about permafrost. Permafrost is ground that has remained frozen for at least 2 consecutive years. In reality, most permafrost has been frozen for thousands or even hundreds of thousands of years. It underlies about a quarter of the land area of the northern hemisphere, vast stretches of Siberia, Canada, Alaska, and parts of China and the Tibetan Plateau. Permafrost can extend to depths of hundreds, or even over 1,000 meters in some places. The top layer, called the active layer, thaws each summer and refreezes each winter. But below that, the ground stays frozen year-round. Within the permafrost, preserved in the cold, are enormous quantities of organic carbon, the remains of plants and animals that lived and died over thousands of years. This carbon is locked away, quiet and still, as long as the ground remains frozen. It is a very large, very patient reservoir. When scientists study the relationship between ice ages and the atmosphere, they think about what are called feedback mechanisms, processes that either amplify or dampen the initial climate signal from Milankovitch cycles. On their own, the changes in Earth's orbit and tilt don't produce enough cooling to explain the full magnitude of ice ages. The solar forcing, as scientists call it, is relatively small. It's the feedbacks, ice albedo feedback, CO2 feedback, methane feedback, ocean circulation changes, that amplify the initial nudge into a full glaciation. Together, these feedbacks act like a very slow amplifier, taking a quiet initial signal and gradually building it into something much larger. This is why ice ages develop over thousands of years rather than decades. Each feedback takes time to engage, and the whole system moves with the enormous inertia of oceans and ice sheets and rock. Gently moving forward, let's think about the role of clouds. Clouds are one of the most complex and uncertain parts of the climate system. They can both warm and cool the surface, depending on their type and altitude. Low, thick clouds reflect incoming sunlight back into space, cooling the surface below them. High, thin clouds trap outgoing heat, warming the surface. During an ice age, the types and distribution of clouds would have been very different from today. Drier air, different atmospheric circulation patterns, and the presence of vast ice sheets all change where and how clouds form. Scientists are still working to understand exactly how clouds respond to climate changes and whether they tend to amplify or dampen temperature swings over glacial cycles. Clouds are one of the last great puzzles of climate science, visible, familiar, and yet still holding many of their secrets close. Water vapor is actually the most abundant greenhouse gas in the atmosphere. It absorbs and re-emits infrared radiation very effectively, and it plays a major role in the greenhouse effect. But water vapor doesn't control the climate the way CO2 does. Instead, it responds to temperature. When the atmosphere warms, more water evaporates from the oceans, increasing the amount of water vapor in the air, which causes further warming, another feedback loop. When the climate cools, the atmosphere holds less water vapor, which allows more heat to escape, causing further cooling. So water vapor amplifies temperature changes in both directions. During ice ages, the cooler, drier atmosphere held less water vapor, which contributed to the overall cooling. It's a quiet, invisible thread in the fabric of the climate, doing its work without being seen. And we can take a moment to notice the quiet movement of water. The ocean is not a uniform body of water. It is layered, with warm, light water floating near the surface and cold, dense water sitting below. These layers don't mix easily. The boundary between warm surface water and cold deep water is called the thermocline, and it acts as a kind of invisible barrier. In tropical regions, the surface water can be 25 or 30 degrees warmer than the water just a few hundred meters below. During ice ages, the surface ocean cooled significantly. Sea surface temperatures in tropical regions may have been 5 to 6 degrees lower than today, and the contrast between surface and deep water changed. This affected how much CO2 the ocean could absorb, how ocean currents moved, and how much moisture evaporated to feed the ice sheets. The ocean's layered structure is a quiet but fundamental part of how ice age cycles work. The North Atlantic is a particularly important region for ice age dynamics. It is here that the Atlantic meridional overturning circulation, the great conveyor belt of ocean water, both begins and ends its surface journey. Warm surface water flows northward from the tropics, releasing heat to the atmosphere and helping to keep northwestern Europe relatively mild. When this water reaches the high latitudes of the North Atlantic, it cools, becomes denser, and sinks to the deep ocean, eventually spreading southward along the ocean floor. During periods of rapid glacial melting, huge amounts of fresh water pour into the North Atlantic from melting ice. This fresh water sits on top of the salty ocean water and prevents it from sinking, potentially disrupting or even shutting down the overturning circulation. When this has happened in the past, it has caused very rapid, geologically speaking, climate shifts around the northern hemisphere. About 12,000 years ago, as the last ice age was drawing to a close and the ice sheets were melting, there was a sudden, unexpected return to cold conditions in the northern hemisphere. This cold period lasted roughly 1,200 years and is called the Younger Dryas, named after an Arctic flower called Dryas octopetala, whose pollen appears in the sediment record from that time. The leading explanation for the Younger Dryas is that a large pulse of meltwater entered the North Atlantic, slowing or disrupting the overturning circulation and reducing the flow of warm water to the north. Temperatures in parts of Europe dropped by perhaps 10 degrees Celsius in just a few decades, extraordinarily fast by geological standards. Then, about 11,700 years ago, the cold ended just as abruptly, and the Holocene interglacial, the warm period we still live in, began. Now, as we continue, let's think about the quiet places where ice forms. Ice sheets form in very specific places. They need high latitudes, where sunlight arrives at a low angle and is therefore less intense. They need enough precipitation, enough snowfall, to build up year after year. And they need cool summers, so that the snow from each winter doesn't completely melt before the next winter adds more. Antarctica and Greenland are the two places on Earth today that meet all of these conditions, and both are covered in thick ice sheets. The Antarctic ice sheet is by far the larger of the two. It contains about 26.5 million cubic kilometers of ice, holding roughly 60% of all the fresh water on Earth. Greenland holds about 3 million cubic kilometers. Together, these two ice sheets represent the remnants of a much larger glacial system, the surviving edges of the ice age that is still, technically, ongoing. Sea ice is different from ice sheets. Ice sheets sit on land. They are made of compressed snow accumulated over thousands of years. Sea ice forms when the ocean surface freezes during winter. It is thin, usually just a meter or two thick, and it forms and melts each year with the seasons. In the Arctic, sea ice covers much of the Arctic Ocean in winter and retreats in summer. In the Antarctic, sea ice forms around the continent each winter, dramatically increasing Antarctica's effective size, and then melts back each summer. Sea ice affects climate through its albedo, reflecting sunlight in summer, and by insulating the ocean surface from the cold air above it in winter. It also affects ocean salinity. When seawater freezes, the salt is mostly excluded from the ice, making the water beneath more saline and denser, which can drive ocean circulation. The Greenland ice sheet sits in a bowl of bedrock. Over hundreds of thousands of years, the weight of the ice has pressed the bedrock down, and the surrounding mountains hold the ice in place. If the Greenland ice sheet were to melt entirely, which would take many thousands of years under any plausible scenario, sea level would rise by about 7 meters. Much of the ice sheet's base is at or below sea level, which makes it somewhat vulnerable to warming from below. But the ice sheet is also very thick, up to 3 kilometers in the center, and it has its own climate system, with cold air pooling above it and suppressing precipitation. The Greenland ice sheet is a quiet, ancient presence, sitting above the storms and the sea, holding most of the world's Greenland in a cold and stillness that has persisted for millions of years. Slowly, gently, the ice rests on the land, patient and still. Antarctica was not always covered in ice. For most of Earth's history, It was a warm continent, at times covered in forests, inhabited by dinosaurs and early mammals. The Antarctic ice sheet began to form about 34 million years ago, when the continent drifted to the South Pole and the Antarctic circumpolar current developed. Before that, warm ocean water could flow around the continent and keep it relatively mild. Once the circumpolar current formed, Antarctica was thermally isolated, cut off from warm water by the endless circulation of cold water around it. CO2 levels were also declining at that time, which added to the cooling. The ice grew slowly, spreading from the mountains toward the coast, until eventually it covered the entire continent. And it has been there ever since, sitting quietly at the bottom of the world, its surface higher than most mountain ranges. There is no need to rush. During the height of the last ice age, about 20,000 years ago, so much water was locked up in ice sheets that global sea levels were roughly 120 to 130 meters lower than they are today. This had profound consequences for the shape of the world. Many areas that are now shallow sea were exposed as dry land. The floor of the North Sea was a grassy plain inhabited by woolly mammoths and humans. The Indonesian archipelago was mostly connected to mainland Asia. Australia and New Guinea were one landmass, and the most famous exposed land bridge of all, Beringia, connected Siberia to Alaska across what is now the Bering Strait. It was across this broad, flat plain that the ancestors of Native Americans first arrived in the Americas, walking gently across land that the sea now covers, following herds of animals into a continent that had never known human footsteps. Beringia was not just a narrow bridge. At its maximum extent, it was a vast, open landscape about 1,000 kilometers wide, stretching between the continents. It had its own ecosystem, cold, dry, dominated by grasses and low shrubs, grazed by woolly mammoths, horses, bison, and giant ground sloths. The climate there was cold but not buried in ice. The region was too dry for large glaciers to form. It was a steppe tundra environment, windswept and treeless, lit by the low Arctic sun. Humans who lived in Beringia thousands of years ago would have seen herds of large animals on the horizon, the flat land stretching in all directions, the sky enormous and pale. Eventually, as the ice retreated and sea levels rose, Beringia was flooded by the Bering Sea. The land bridge quietly slipped beneath the water, leaving only the memory of a crossing. Let's take a quiet moment to think about the animals of the Ice Age. The woolly mammoth is perhaps the most iconic animal of the last Ice Age. It was a close relative of today's Asian elephant, adapted to the cold with a thick coat of fur, a dense undercoat for insulation, small ears to reduce heat loss, and a high, domed skull that anchored large neck muscles. Mammoths used their long, curved tusks to sweep away snow and ice to reach the grass below. They lived across a vast range, from Europe and Siberia to North America, for hundreds of thousands of years. The last mainland woolly mammoths disappeared about 10,000 years ago, as the Ice Age ended and their cold grassland habitat shrank. But a small, isolated population survived on Wrangel Island in the Arctic Ocean until about 4,000 years ago, contemporary with the Egyptian pyramids. They were quiet, cold-adapted, and extraordinarily patient animals. The woolly rhinoceros was another large mammal of the Ice Age, roughly the same size as today's white rhinoceros, covered in thick reddish-brown fur. It had two horns, the front one very long, sometimes over a meter, which it used to sweep snow aside to reach vegetation. Woolly rhinos ranged across Europe and Asia during the cold periods. Like the mammoth, they are known from cave paintings left by early humans, who clearly encountered them and found them significant enough to record on stone walls by firelight. Remarkably preserved frozen carcasses of woolly rhinos have been found in Siberian permafrost, with skin, fur, and even stomach contents intact, allowing scientists to know exactly what these animals looked like and what they ate. The permafrost preserved them the way time is preserved in a very cold, very dark place, without rushing, without change. Caves across Europe contain paintings made by humans who lived during the last ice age. The most famous, like those at Lascaux in France and Altamira in Spain, date back 15,000 to 36,000 years. The artists painted with ochre, charcoal, and manganese, depicting horses, bison, aurochs, deer, mammoths, and rhinoceroses in remarkable detail. Some of the images show animals in motion, multiple legs suggesting movement, bodies twisted in perspective. The caves were not ordinary living spaces. They were likely places of ceremony or meaning, their inner passages sometimes difficult to navigate, the paintings placed in the deepest and most hidden chambers. Sitting in the flickering light of a small lamp, painting by hand on cold stone, the Ice Age artists left something extraordinary, a quiet conversation across 40,000 years, speaking not in words but in images of the animals they knew. Gently moving forward, let's think about what the forests were doing. During the last glacial maximum, the distribution of forests around the world was very different from today. Much of what is now temperate forest, the woods of Europe, North America, and parts of Asia was tundra, steppe, or desert. The trees hadn't disappeared, but they had retreated to refugia, small, sheltered areas where the climate was slightly milder, where forests persisted in isolated pockets. The Amazon rainforest, which we tend to think of as unchanging and ancient, may have been much reduced during the glacial maximum, fragmented into separate forest refugia separated by savanna and scrubland. When the climate warmed at the end of the Ice Age, forests expanded from these refugia, spreading out across the warming landscape, refilling the temperate regions with trees. The forests of Europe and North America today are only a few thousand years old in their current configurations, young, in geological terms, still finding their shape. Pollen is extraordinarily durable. A pollen grain's outer wall is made of one of the most chemically resistant natural substances known, called sporopollenin. It survives in soils and lake sediments for tens of thousands of years without decomposing. And because different plant species produce distinctively shaped pollen grains, scientists can examine pollen preserved in ancient lake sediments or peat bogs and determine which plants were growing in the area at any given time in the past. This is called palynology, or pollen analysis. By tracing how the proportions of different pollen types change up through a sediment core, scientists can reconstruct how the vegetation of a region changed over time, tracking the advance and retreat of forests, grasslands, and tundra in response to the Ice Age cycles. The pollen doesn't know it's being read. It simply drifted down, settled, and waited, and we can take a moment to notice how gently the land was shaped. A U-shaped valley is one of the clearest signs that a glacier has passed through. River valleys tend to be V-shaped, carved by water cutting downward in a narrow channel. But glaciers are wide, and they grind everything, the valley floor and the valley sides equally. The result is a broad, flat-bottomed valley with steep, smooth sides, the classic U-shape seen in the Scottish Highlands, the Alps, the Norwegian fjords, and many other glaciated landscapes. The scale of these valleys is often breathtaking, not because they are dramatic, but because of the sheer quiet enormity of the work that made them. A glacier that filled a valley kilometers wide and hundreds of meters deep, moving with enormous patience for thousands of years, eventually left behind a space of openness and calm. The ice is gone, but the shape it left is there forever. Fjords are perhaps the most dramatic expression of glacial erosion. They form when a glacier carved a valley below sea level, and then, when the ice retreated, the sea flooded in to fill it. The result is a long, narrow, deep inlet of the sea, with steep walls rising on either side. Norway has more than 50,000 islands and thousands of fjords, carved by glaciers during the last ice age. Some Norwegian fjords are extraordinarily deep. The Sonefjord, the longest and deepest in Norway, reaches depths of over 1,200 meters in places, making it deeper than most of the surrounding sea. At its head, the fjord is surrounded by mountains and waterfalls and quiet villages. The water is very deep and very still below the surface, sheltered from the open sea by the glacier-carved walls. It is one of the calmest landscapes on Earth, made by one of the most powerful forces. Hanging valleys are another beautiful feature left by glaciers. When a large glacier occupies a main valley and a smaller glacier feeds into it from a side valley, the two glaciers erode at different rates. The main glacier carves its valley much deeper than the smaller tributary glacier. When the ice retreats, the tributary valley is left high on the side of the main valley wall, its floor hanging far above the valley floor below. A waterfall often develops, dropping from the mouth of the hanging valley down to the main valley below. Yosemite Valley in California is full of hanging valleys and their waterfalls, Yosemite Falls, Bridal Veil Fall, and others all drop from hanging valleys formed by tributary glaciers into the main canyon carved by the larger Merced Glacier. Each waterfall is a quiet monument to the difference in scale between the ice that made these spaces. Now, as we continue, let's rest on the idea of the Ice Age landscape. During the last glacial maximum, the landscape at the edges of the great ice sheets would have been a periglacial environment, not buried under ice, but deeply affected by the cold. In periglacial regions, the ground freezes and thaws repeatedly, creating distinctive landforms. Polygonal patterns form in the soil, where cycles of freezing and thawing organize material into geometric networks of stone and earth visible from above. Pingos, large mounds of earth-covered ice, grow slowly from the ground, sometimes reaching heights of tens of meters, as water migrates upward and freezes beneath a growing dome. Stone stripes and sorted circles appear on slopes and flat ground. The whole landscape is slowly, quietly rearranging itself in response to the cold, ordering itself into patterns that look almost deliberate, almost designed. They are the natural geometry of the periglacial world, repeated across vast areas of the cold landscape. Moraines are the piles of rock, gravel, and sediment that glaciers deposit. As a glacier moves, it picks up material from the ground below and the valley walls, carrying it forward. When the glacier melts or stops advancing, this material is deposited. A terminal moraine marks the furthest extent of a glacier, a ridge of debris left at the glacier's snout. Lateral moraines run along the sides of a valley where the glacier deposited material from the valley walls. Medial moraines form in the middle of a glacier where two glaciers merge, their lateral moraines combining into a single dark stripe running down the center of the ice. Moraines can be subtle, gentle ridges across a landscape that might easily be mistaken for natural hills. Or they can be dramatic, steep-sided ridges of jumbled boulders and gravel that clearly mark a boundary between glaciated and unglaciated terrain. Either way, they are quiet markers of where the ice once was. The Laurentide ice sheet was the great ice sheet that covered most of North America during the last glacial maximum. At its peak, it was about 3 kilometers thick over Hudson Bay, and it extended as far south as the Ohio River Valley and the Missouri River. Its weight depressed the crust so much that Hudson Bay is still recovering, still rising, from the weight of ice that melted 10,000 years ago. The Laurentide ice sheet scoured the landscape of Canada so thoroughly that it removed almost all the soil that had developed since the previous interglacial. The thin, rocky soils of the Canadian Shield today are partly a result of this scouring. The ice took everything away and left bare rock, onto which new soil is only slowly accumulating. The ice was, in a sense, both a destroyer and a resetter, stripping the land bare so that new ecosystems could build from the beginning. Slowly, gently, the story of the ice continues. Loess is a very fine-grained sediment, a silted dust, that was blown by winds from the edges of ice sheets and deposited over large areas of the surrounding landscape. As glaciers ground rock into powder and glacial rivers carried the fine sediment to outwashed plains, strong katabatic winds blowing off the ice picked up this rock flour and transported it far downwind, settling it in thick blankets over the surrounding countryside. Some of the most fertile agricultural soils in the world are loess deposits from the last ice age. The deep black soils of the American Midwest, the Corn Belt, are built on thick loess deposits. The fertile plains of northern China, Ukraine, and Argentina similarly owe their productivity to ice age winds that deposited this fine glacial flour over vast areas. The ice age, in its slow and patient way, was creating the conditions for agriculture and civilization to eventually arise. There is no need to rush. The sun is a middle-aged star, about halfway through its main sequence life. It has been shining for about 4.5 billion years and will continue to shine for roughly another 5 billion. Over that time, the sun gradually becomes slightly brighter, about 10% brighter for every billion years. This means that in the deep past, the sun was fainter than it is today. For billion years ago, the sun was only about 70% as bright as it is now. And yet geological evidence suggests that the early Earth was not frozen. This discrepancy is known as the faint young sun paradox. The resolution likely involves a denser atmosphere with much higher concentrations of greenhouse gases, CO2 and methane, in the early Earth's atmosphere, which compensated for the fainter sun and kept the surface warm enough for liquid water. Stars like the sun don't shine with a perfectly steady light. There are small cycles of activity, the most familiar being the 11-year sunspot cycle. Sunspots are darker, cooler areas on the sun's surface associated with intense magnetic activity. During periods of high sunspot activity, the sun actually emits slightly more total energy, about 0.1% more, even though the sunspots themselves are darker, because the surrounding areas become brighter. The effect of the solar cycle on Earth's climate is real, but very small. There have been periods in history, like the Maunder minimum in the late 17th century, when sunspot activity was suppressed for decades. This corresponded with a period of slightly cooler temperatures in Europe and North America, sometimes called the Little Ice Age. But the effect was modest, a global cooling of perhaps 0.1 degrees Celsius, compared to the multi-degree swings of true glacial cycles. Let's take a quiet moment to think about the sky at night, long ago. During the last ice age, the night sky would have looked almost exactly as it does today. The positions of the stars changed so slowly, over timescales of tens of thousands of years for precession, millions of years for the proper motion of stars, that 20,000 years of elapsed time would make only subtle differences in the arrangement of constellations. The Milky Way would have arched across the sky, just as it does now. The same stars would have risen and set. Humans living near the edges of the ice sheets, people who were anatomically and cognitively modern, just like us, would have watched the same sky, noticed the same planets wandering against the fixed stars, wondered about the same questions. The sky is one of the great continuities between us and all the people who lived before, stretching back through the Ice Age and beyond. The aurora borealis, the northern lights, would have been a familiar sight to people living near the Ice Age ice sheets. The aurora occurs when charged particles from the sun, the solar wind, interact with Earth's magnetic field and are funneled toward the poles. The particles collide with atoms in the upper atmosphere, exciting them and causing them to emit light in curtains and ribbons of green, red, and sometimes purple. During the Ice Age, the magnetic poles were in slightly different positions than today, and the auroral oval, the zone where the lights appear, would have been positioned differently over the landscape. But the lights themselves would have been just as beautiful, just as mysterious. To people who had no explanation for them, the lights moving silently across the cold sky must have been one of the most extraordinary sights in the world. Earth's magnetic field is generated by the movement of molten iron in the planet's outer core. The field extends far out into space and deflects most of the solar wind, the stream of charged particles constantly flowing from the sun. Without this magnetic shield, the solar wind would gradually strip away the atmosphere and bombard the surface with radiation, as has happened to Mars, which lost its magnetic field billions of years ago. The magnetic field is not perfectly stable, it wanders, and it has reversed polarity hundreds of times in Earth's history. During a reversal, the field weakens significantly before reforming with reversed polarity. There is no evidence that magnetic reversals directly trigger ice ages, but they do leave signatures in rocks that help scientists date geological formations and trace the history of the ocean floor. The magnetic field is another quiet, invisible protection that makes the surface habitable. Gently moving forward, toward the question of what sets ice ages apart. Not all cold periods in Earth's history are the same. Scientists distinguish between icehouse periods, long intervals when the planet has permanent ice at one or both poles and is susceptible to glacial cycles, and greenhouse periods, long intervals when the planet is too warm for permanent polar ice. For most of Earth's history, the planet has been in a greenhouse state, with no ice at the poles. We are currently in an icehouse period, which began when Antarctica became permanently glaciated about 34 million years ago. Icehouse periods seem to be associated with low atmospheric CO2 concentrations and with continental configurations that allow cold, deep water to form at the poles. The current icehouse period is one of the most prolonged in the last half-billion years, and the ice ages within it are driven by the Milankovitch cycles we've been exploring all evening. And we can take a moment to notice the quiet complexity of the world. The silicate weathering cycle is one of the longest-acting thermostats in Earth's climate system. When silicate rocks, the most common type of rock, are exposed to rain and air, they weather chemically. CO2 dissolved in rainwater forms a weak carbonic acid, which reacts with the rock minerals and slowly dissolves them. The products wash into rivers and eventually into the ocean, where marine organisms use them to build calcium carbonate shells. When those organisms die, their shells sink to the seafloor and are eventually buried, locking away carbon. So weathering removes CO2 from the atmosphere over millions of years. But volcanic eruptions add CO2 back. The balance between these two processes, weathering removing carbon, volcanism adding it, controls atmospheric CO2 over geological timescales. It is an extremely slow process, operating over millions of years, but it sets the stage on which the faster ice age cycles play out. The ocean contains about 50 times more CO2 than the atmosphere. Most of this is dissolved CO2 or carbonate ions, not free gas. The ocean and the atmosphere are constantly exchanging CO2. The ocean absorbs CO2 when concentrations are high in the atmosphere and releases it when concentrations drop. How much CO2 the ocean can hold depends on its temperature. Colder water can dissolve more CO2. During ice ages, as the ocean cooled, it absorbed more CO2 from the atmosphere, which further cooled the planet. This is another gentle feedback loop, operating over centuries and millennia, the ocean quietly drawing down the greenhouse gas as it cools, amplifying the glaciation. The ocean is a vast, slow chemical system, always seeking equilibrium with the atmosphere, always adjusting its carbon content to match the conditions. Iron fertilization is a fascinating process in the ocean. Phytoplankton, the tiny photosynthetic organisms that form the base of the ocean food web, need iron to grow. In much of the open ocean, iron is scarce, limiting the growth of phytoplankton even when other nutrients are abundant. During ice ages, more dust was blown off the expanded deserts and bare glacial plains into the ocean, delivering iron to otherwise iron-limited regions. This may have stimulated large blooms of phytoplankton, which absorbed CO2 from the atmosphere during photosynthesis. When the phytoplankton died, their carbon-rich bodies sank to the deep ocean, effectively transferring carbon from the atmosphere to the seafloor. This biological pump may have contributed to the lower CO2 levels of glacial periods, acting as another quiet amplifier of the Ice Age cooling. Now, as we continue, let's think about the dust. During glacial periods, the world was dustier, much more exposed, dry, bare land, no forests, no soil-holding vegetation over vast areas, combined with stronger winds to produce enormous amounts of airborne dust. Ice cores from Antarctica and Greenland show dust concentrations during glacial periods that are 25 to 50 times higher than during interglacials. This dust came from the great deserts and plains of Africa, Asia, and North America. It traveled thousands of kilometers before settling. The dust itself affected climate by blocking and scattering sunlight, and by fertilizing the ocean, as we just discussed. It also darkened the ice in some regions, changing its albedo slightly. The dusty, gray-tinted ice of the last glacial maximum would have looked different from the clean white ice of the interglacial. The world, in the depths of an ice age, was not just cold. It was also gray and windy and full of a slow, quiet movement of particles through the air. Dust storms today give us a small window into what the glacial world may have been like. The Sahara, the world's largest hot desert, generates enormous dust plumes that travel across the Atlantic Ocean. Satellite images show these rivers of dust crossing thousands of kilometers of open sea. The dust that reaches the Amazon actually fertilizes the rainforest, providing phosphorus that the nutrient-poor tropical soils lack. This is a connection few people think about. The fertility of the Amazon partly depends on dust blowing from the Sahara. During the last ice age, the Sahara was even larger and drier than it is today, and the dust it produced was even more abundant. The world's material, its rocks, its soils, its carbon was constantly being moved by wind, water, and ice, redistributed slowly but constantly across the surface. Salt is another substance that moves between different reservoirs as ice ages cycle. When sea ice forms, it expels salt into the surrounding ocean water, making that water denser and helping to drive the deep ocean circulation. When sea ice melts, fresh water is released into the ocean. On a larger scale, when ice sheets build up, they lock away fresh water and the oceans become slightly salter. When ice sheets melt, vast amounts of fresh water pour into the oceans, diluting the salinity. These changes in ocean salinity affect the density of water, which affects circulation patterns, which affects the distribution of heat around the planet. Salt, moving between ice sheets and oceans, is another quiet thread in the enormously complex tapestry of ice age dynamics. Slowly, gently, everything is connected. The concept of teleconnections in climate science refers to the way climate changes in one region can influence conditions in distant parts of the world, sometimes on the other side of the planet. Ice age climate changes in the northern hemisphere, the growth of ice sheets, changes in ocean circulation, shifts in atmospheric pressure, are recorded in sediments and ice cores from the Antarctic, the tropics, and the Pacific. The monsoon systems of Asia and Africa weakened during glacial periods. The tropical Pacific showed different temperature patterns. Changes in the North Atlantic reverberated through atmospheric circulation all the way to the southern hemisphere. The climate system is deeply interconnected, not a collection of isolated regional climates, but a single, global system in which distant parts communicate through the atmosphere and ocean, slowly but surely, across thousands of kilometers. There is no need to rush. Modern humans, Homo sapiens, evolved in Africa about 300,000 years ago. For most of our existence as a species, we have lived through Ice Age conditions. The last glacial period lasted from roughly 100,000 years ago to 11,000 years ago. During that time, humans migrated out of Africa, reached Europe, Asia, Australia, and eventually the Americas. They adapted to radically different environments, from the cold steppes near the ice sheets to tropical forests and semi-arid grasslands. Our species is, in a very real sense, a child of the Ice Age. Our bodies, our brains, our social structures all evolved in the context of a cold, fluctuating climate. The warmth and stability of the Holocene, the last 11,000 years, is an unusual interlude in our species' long experience with a variable and often cold world. Neanderthals, our closest extinct relatives, lived in Europe and Western Asia for over 400,000 years, enduring multiple glacial and interglacial cycles. They were powerfully built, with large brow ridges and broad noses, adapted to the cold. They hunted large mammals, used fire, buried their dead, and may have made jewelry and used ochre for body decoration. For tens of thousands of years, Neanderthals and modern humans overlapped in Europe, and we know from ancient DNA that they interbred, because most people of non-African descent today carry about 1 to 2% Neanderthal DNA. The Neanderthals disappeared about 40,000 years ago, during a period of rapid climate fluctuation. Whether climate change, competition with modern humans, or some combination of factors led to their extinction is still debated, gently and carefully, by scientists. Let's take a quiet moment to think about early humans and fire. Control of fire was one of the most transformative technologies in human history. Fire provided warmth in cold climates, light in the darkness, protection from predators, and the ability to cook food, which made calories more bioavailable and may have fueled the growth of larger brains. The earliest convincing evidence for controlled use of fire by human ancestors dates to about 1 million years ago, at sites in South Africa. By the time of the last ice age, fire use was universal among human populations. For people living near the ice sheets in Europe and Asia, fire was not a luxury but a necessity. Without it, survival at those latitudes during the long, dark Ice Age winters would have been impossible. The warmth of a fire, the light it cast, the food cooked over it, these were the foundations of Ice Age human life. The megafauna extinctions, the disappearance of most of the world's large mammals, happened at the end of the last Ice Age, roughly 10 to 12,000 years ago, and are one of the great puzzles of prehistory. In North America alone, at least 35 genera of large mammals went extinct in a geologically short period of time. Mammoths, mastodons, giant ground sloths, horses, camels, saber-toothed cats. American lions, short-faced bears, all gone within a few thousand years. Similar waves of extinction happened in South America, Australia, and eventually on islands as humans arrived. The debate over the relative roles of climate change, the end of the Ice Age brought profound ecological changes, versus hunting by humans has continued for decades. Most scientists today think both played a role, with the details varying by region and species. The world at the end of the Ice Age was a quieter world, with fewer and smaller animals, gently moving forward toward the long perspective. Human civilization, agriculture, cities, writing, metalworking developed entirely within the Holocene, the warm interglacial we currently inhabit. The relative climate stability of the last 10,000 years was essential for the development of agriculture. Farming requires predictable seasons, reliable rainfall, and soils that stay in one place. The wild swings of a glacial climate, droughts, cold snaps, rapid shifts in vegetation, would have made it much harder to develop and maintain agricultural systems. In a sense, civilization is a Holocene creation. All of recorded history, every kingdom, every empire, every city, every written word, has unfolded within this brief window of unusual climatic stability. It is humbling to think of how contingent our world is on the warmth and calm of this particular moment in Earth's long history. The most recent fully developed interglacial before ours was called the Eemian, and it lasted from about 129,000 to 116,000 years ago. During the Eemian, global temperatures were slightly warmer than today, perhaps 1 to 2 degrees Celsius warmer on average, and sea levels were several meters higher, because the Greenland ice sheet was smaller and parts of West Antarctica had melted. Hippopotamuses lived in the rivers of Britain. Forest covered much of the land that is now tundra in Siberia and Canada. The climate was gentle and warm, and the ice sheets had retreated to positions smaller than today. Then, slowly, the Milankovitch forcing changed, summers in the high northern latitudes began to cool, and the long descent into the last glacial period began. Over thousands of years, quietly, almost imperceptibly, the ice began to build again. And we can take a moment to notice the deep stillness of the ocean floor. The floors of the ocean are covered in sediment, the slow rain of particles that drift down from the surface over millions of years. Shells of tiny organisms called foraminifera make up a large part of this sediment. When foraminifera are alive, they build their shells from calcium carbonate, incorporating the chemicals dissolved in the seawater around them. The ratio of different oxygen isotopes in their shells depends on the temperature of the water they lived in. When foraminifera die, their shells sink to the seafloor and are incorporated into the sediment record. Scientists can drill into ocean sediment cores and analyze the isotopic composition of foraminifera shells layer by layer, reconstructing the temperature of the surface ocean going back millions of years. This sediment record is, in many ways, the most complete and detailed record of past ice ages that we have. Foraminifera are extraordinary little organisms. They are single-celled, yet they build intricate shells that can be quite beautiful: spiral coils, spherical chambers arranged in chains, simple cups or umbrellas. Different species prefer different water temperatures, and their assemblages shift as the ocean warms or cools. During cold periods, cold water species of foraminifera dominate the high-latitude surface ocean. During warm periods, warm water species extend poleward. By counting the relative proportions of warm and cold water species in sediment layers, scientists can estimate past surface ocean temperatures with surprising precision. The foraminifera had no intention of recording the history of ice ages. They were simply living and dying and sinking to the bottom, as they had done for hundreds of millions of years. But their tiny shells hold an enormous amount of information about the past. The ocean sediment record goes back much further than the ice core record. Where ice cores give us detailed, year-by-year information back about 800,000 years, ocean sediments preserve a more smoothed but longer record, going back tens of millions of years. From this record, scientists can trace the development of the current icehouse climate, seeing when the Antarctic ice sheet first formed. when the Arctic began to glaciate, and how the rhythm of glacial cycles has changed over time. In the last 2.5 million years, the dominant period of glacial cycles has been about 100,000 years, matching the eccentricity cycle. But before about 800,000 years ago, the dominant period was closer to 41,000 years, matching the obliquity cycle. Something changed in the mid-Pleistocene, around 800,000 years ago, to shift the dominant cycle. Scientists are still investigating what that transition involved. Now, as we continue, let's rest on the thought of the world's long cold memory. The mid-Pleistocene transition, as it is called, is one of the intriguing puzzles of Ice Age science. Before about 1.25 million years ago, glacial cycles were shorter, roughly 41,000 years, and ice sheets were smaller. Then, gradually, over a period of about 400,000 years, the cycles lengthened to roughly 100,000 years and ice sheets became larger. The external forcing, the Milankovitch cycles, didn't change. The obliquity cycle is still 41,000 years. But somehow the climate system switched to responding preferentially to the weaker 100,000-year eccentricity cycle. Various explanations have been proposed: a long-term decline in atmospheric CO2, the erosion of regolith beneath the ice sheets exposing harder bedrock, or changes in the ocean circulation. The answer isn't fully settled, and it remains one of the most interesting open questions in paleoclimatology. Coral reefs also preserve records of past sea levels and ocean temperatures. Corals build their skeletons from calcium carbonate, and the chemical composition of those skeletons, including isotopic ratios and the presence of certain trace elements like magnesium, reflects the temperature and salinity of the water in which the coral grew. When sea level falls during a glacial period, shallow water corals that were living below sea level are exposed and die. When sea level rises during an interglacial, new reefs establish themselves at the new sea level. By dating coral skeletons from different depths along coastlines, scientists can track how sea level has changed over the past few 100,000 years, providing independent confirmation of the ice core and ocean sediment records. The reefs are beautiful, complex ecosystems that are also, quietly, very detailed archives of ocean history. Speleothems, cave formations, are another remarkable archive of past climate. Stalactites hang from cave ceilings. Stalagmites grow up from cave floors. Both are built layer by layer as mineral-rich water seeps through the overlying rock and drips into the cave. The growth of speleothems depends on the amount of rainfall, the temperature, and the vegetation above, all of which change with the climate. By analyzing the layers of calcite in speleothems and dating them precisely with uranium-thorium dating, scientists can reconstruct records of precipitation and temperature going back hundreds of thousands of years. Some Chinese cave systems have yielded records of monsoon strength that extend back over 500,000 years, clearly showing the influence of Milankovitch cycles on the strength of the Asian monsoon. The cave is dark and still, and it has been recording time in its slow, dripping way for all of that. Slowly, gently, the Earth keeps its records everywhere. Lake sediments provide yet another window into past climates. In many lakes, sediments accumulate in thin, paired layers called varves, one dark layer from summer and one light layer from winter deposited each year. By counting varves, scientists can create precise chronologies going back thousands of years, like tree rings but in water. The thickness of varve layers varies with climate. More snowmelt in warm years deposits thicker summer layers. The types of pollen preserved in the sediment record the surrounding vegetation. Microscopic algae and other organisms leave their shells in the sediment, recording the temperature and chemistry of the water. Lake Suigetsu in Japan has yielded an extraordinary VARV record going back about 60,000 years, which has been used to precisely calibrate radiocarbon dating for that entire period. Still water, slowly accumulating its layers, quietly building an archive of time. There is no need to rush. Ice ages don't end the way they begin. They begin very slowly, the gradual accumulation of ice over tens of thousands of years, the slow cooling of the oceans, the quiet spread of tundra and steppe across previously forested landscapes. But they tend to end somewhat faster, a process called deglaciation or glacial termination. The warming that ends a glacial period is still slow by human standards. It takes thousands of years, but it is faster than the cooling. This asymmetry is partly because the feedbacks that amplify warming, ice albedo feedback, CO2 release from warming oceans, methane release from thawing permafrost, can operate somewhat more rapidly than the feedbacks that build ice. The gradual buildup of ice is a slow dripping of the tap. The melting can be, geologically, more like a slow pour. Still slow, still gentle, but somehow more eager than the cold that preceded it. The last deglaciation, the end of the last ice age, began about 20,000 years ago when the northern hemisphere summer insolation started to increase due to Milankovitch forcing. Gradually, over several thousand years, the ice sheets began to thin. Meltwater lakes formed at the margins of the ice. Glacial rivers carried enormous quantities of sediment into the oceans. Sea levels began to rise slowly at first, then more quickly, then slowly again. The coastlines of the world shifted, inundating low-lying areas that had been dry land. Forests and grasslands advanced northward into areas previously covered in tundra. The megafauna disappeared, and then, roughly 11,000 years ago, the climate settled into the warm, stable Holocene, and the conditions were set for everything that human civilization would go on to build. Let's take a quiet moment to think about meltwater and rising seas. As the great ice sheets of the last glacial maximum melted, they released an almost incomprehensible volume of water into the oceans. Sea level rose by about 120 meters in total, from its glacial low to its current level. The bulk of this rise happening between about 20,000 and 7,000 years ago. The rate of sea level rise was not constant. There were periods of rapid rise, called meltwater pulses, when the ice retreated particularly quickly and enormous amounts of water entered the ocean in a geologically short time. One such event, called Meltwater Pulse 1A, around 14,600 years ago, may have raised sea level by 10 to 15 meters in less than 500 years. These rapid changes in sea level would have flooded coastal areas, altered ocean circulation, and changed the geography of the world in ways that people living at the time would have experienced directly. The flooding of Beringia, the land bridge between Asia and North America, happened gradually as sea levels rose. The first areas to flood were the lowest lying parts of the shallow Bering Sea shelf. By about 11,000 years ago, the connection between the continents was severed, and the Bering Strait had opened. Similarly, what is now the English Channel, separating Britain from France, was flooded as sea levels rose. Until about 8,000 years ago, Britain was connected to the European mainland by a low-lying plain called Doggerland. As sea levels rose, Doggerland was gradually inundated, becoming shallower and eventually disappearing beneath the North Sea. Fishermen in the North Sea have occasionally brought up bones of land mammals and fragments of ancient trees from the seafloor, remnants of a landscape that once existed there, quiet and dark beneath the cold water. The Black Sea has an interesting deglaciation story. During the glacial maximum, sea levels were low, and the Black Sea was an isolated freshwater lake, much smaller than today, around 8,400 years ago. as the Mediterranean Sea rose with global sea levels. Salt water from the Mediterranean may have breached the Bosphorus sill, the natural barrier at what is now Istanbul, and poured into the Black Sea basin. If this happened, the flooding would have been dramatic, a great inrush of salt water into the freshwater lake, raising the Black Sea level and transforming its ecosystem. Some researchers have proposed this event as the basis for ancient flood myths, including the story of Noah. The hypothesis is debated, and the details are still being worked out, but the basic idea that the end of the Ice Age brought real, dramatic changes to coastlines and water bodies is well established, gently moving forward toward what comes after the ice. As ice sheets melted and retreated, they left behind a landscape that was initially barren. Scraped rock, bare sediment, cold meltwater lakes. But life moved in quickly. Geologically speaking, mosses and lichens established themselves first, breaking down the rock and beginning to build soil. Then grasses and sedges. Then dwarf willows and birches in sheltered spots. Then gradually taller shrubs, and eventually forests. As the soil deepened and the climate warmed, this ecological succession, the progressive development of ecosystems in newly deglaciated terrain, can still be observed today. In places where glaciers are retreating, the foreland of a retreating glacier, exposed over decades, shows this succession compressed in space. Bare rock near the current glacier terminus, then moss and lichen, then grasses, then shrubs, then small trees. A miniature version of what happened across entire continents over thousands of years. Reindeer, caribou in North America, are one of the most Ice Age-adapted large mammals still alive today. They have wide, flattened hooves that act like snowshoes, allowing them to walk on soft snow. Their hooves also have a sharp edge for digging through snow to reach the lichen below. Their coats are extraordinarily insulating. Each hair is hollow, trapping air for insulation, and the dense underfur provides additional warmth. Their noses pre-warm cold air before it reaches the lungs. They are the only deer species in which both sexes have antlers. Reindeer are highly migratory, traveling enormous distances between summer and winter ranges, following the edge of the productive tundra as it shifts with the seasons. They are in many ways perfectly tuned to the cold, shifting landscape left by the retreating ice. Living examples of Ice Age adaptation that persist into our warmer world. And we can take a moment to notice the long arc of time, based on Milankovitch cycles alone. Without human influence, the next glacial period would likely begin in about 50,000 years. The orbital configuration is currently moving slowly away from conditions favorable for glaciation. The obliquity is near a midpoint in its cycle and heading toward values that favor more moderate seasons. The combination of orbital factors that drive glaciation won't align again for a very long time. However, human activities have significantly increased atmospheric CO2 from pre-industrial levels of about 280 parts per million to over 420 parts per million today. This elevated CO2 may delay the onset of the next glaciation for hundreds of thousands of years, or prevent it entirely within the current orbital regime. In altering the carbon cycle, human civilization may have inadvertently extended the current interglacial far beyond its natural duration. The relationship between CO2 levels and Ice Age onset has been modeled in various ways. Some research suggests that for a glaciation to begin under the current orbital configuration, CO2 would need to drop to around 240 parts per million or below, well below today's levels. Given that human emissions have pushed CO2 to 420 parts per million and rising, the conditions for the next glaciation have been effectively forestalled for the foreseeable future. This is a profound thought, that human activities, which have accelerated in the span of just a few centuries, have altered a geological process that operates on 100,000-year timescales. The next ice age, which would have begun in a quiet, inevitable way 50,000 years from now, may now never come, at least not in the way the Milankovitch cycles alone would have delivered it. The last time CO2 was as high as it is today, about 3 to 5 million years ago, during the Pliocene epoch, sea levels were several meters higher than today, and temperatures were 2 to 3 degrees Celsius warmer. On a global average, the Arctic was largely ice-free in summer. Forests grew in areas that are now tundra. These past warm periods, called analogs, give scientists a sense of what the planet might look like in a warmer future. But the Pliocene was not identical to the present. The continents were in slightly different positions. The solar output was slightly different, and the seasonal distribution of sunlight was different. Still, the Pliocene is a useful reference point, a quiet glimpse at what the Earth looks like when CO2 concentrations are similar to today's, given enough time for the full climate system to equilibrate. Now, as we continue, let's rest on the idea of what ice ages mean for life. Ice ages are not simply destructive events. They're also drivers of evolution and diversification. As ice sheets advance and retreat, they repeatedly fragment populations of plants and animals into isolated refugia, where they evolve independently in response to local conditions. When the ice retreats and the populations expand again, they bring with them new genetic variation. Sometimes, these separated populations have diverged enough to become new species. The cichlid fish of the African Great Lakes, the diverse bird fauna of the Amazon, and the richness of plant life in the Cape Floristic region of South Africa may all owe some of their diversity to the fragmentation and reconnection of populations driven by ice age climate cycles. The ice ages were not just cold interludes. They were engines of biological diversity, quietly reshaping the tree of life. With every advance and retreat, the concept of glacial refugia, the sheltered areas where species survived during glacial periods, is important for understanding the current distribution of life on Earth. Many plant and animal populations in Europe, for instance, trace their ancestry back to populations that survived the last glacial maximum in refugia in Iberia, Italy, and the Balkans, areas that were warmer and had more diverse habitats during the last glacial maximum than the ice-covered north. As the ice retreated, these populations expanded northward, colonizing newly available land. Different refugia produced different genetic lineages, and the mixing of these lineages, as populations expanded, explains much of the genetic diversity we see in European species today. The hedgehogs, the bears, the oaks, the butterflies of northern Europe all carry in their genes the story of their ice age journey from warm southern refugia. Seeds are extraordinary objects. They are packages of genetic information, stored energy, and protective coating, capable of surviving conditions that would destroy the parent plant. Many seeds can remain viable for years, decades, or even centuries. In the right conditions, Arctic lupin seeds, recovered from permafrost in the Yukon, were found to be over 10,000 years old and still germinated successfully. The oldest seeds ever to sprout, seeds allowed plants to survive the ice ages in refugia and then spread rapidly. When conditions improved, they can be carried by wind, water, birds, and mammals across vast distances. The ability to disperse as seeds and to survive dormant for long periods, was essential for plant species to track the shifting climate across the ice age cycles. A seed is a very patient thing, a small, quiet vessel carrying the future. Trees have annual growth rings. Each year, a tree adds a layer of wood, forming a visible ring. In cross-section, wide rings indicate favorable growing years, with warm temperatures and adequate moisture. Narrow rings indicate stress years. By reading these rings, scientists can reconstruct year-by-year records of past climate going back thousands of years. A technique called dendrochronology. Long-lived trees, like the Great Basin bristlecone pine, which can live for over 5,000 years, provide direct climate records from their rings by overlapping ring records from living and dead trees. Scientists have constructed continuous chronologies going back over 11,000 years. While tree rings don't directly record the deep time of ice ages, they capture the climate variability of the Holocene, the warm period within which all of recorded human history has occurred. In remarkable detail, slowly, gently, time is recorded everywhere. In the quietest places, there is no need to rush. The concept of residence time in climate science refers to how long a substance stays in a particular part of the Earth system before being removed or transformed. Carbon dioxide, once added to the atmosphere, has a long residence time. The bulk of a pulse of CO2 persists in the atmosphere for hundreds to thousands of years. Water vapor, by contrast, cycles in and out of the atmosphere very quickly. The average water vapor molecule stays in the atmosphere for only about 9 to 10 days before precipitating as rain or snow and returning to the surface. These different residence times are why water vapor amplifies temperature changes quickly, but doesn't drive them, while CO2 drives long-term climate changes. Over centuries and millennia, the atmosphere is a mixture of substances, each with its own pace, its own rhythm of cycling through the Earth system. The phosphorus cycle is another of the Earth's quiet, slow cycles. Phosphorus is an essential nutrient for life. It is part of DNA, cell membranes, and the energy-carrying molecule ADP. Unlike carbon and nitrogen, phosphorus doesn't have a significant atmospheric component. It cycles through rocks, soils, water, and living things, entirely in the liquid or solid phase. Phosphorus is released from rocks by weathering, carried by rivers to the ocean, incorporated by marine organisms into their tissues and shells, and eventually deposited in ocean sediment over millions of years. Tectonic processes can uplift this sediment back into mountains, where weathering begins the cycle again. It is an extraordinarily slow cycle, operating over millions of years. Ice ages accelerate weathering by exposing fresh rock. The glaciers grind the rock to powder, which weathers rapidly when the ice retreats, potentially releasing bursts of phosphorus to the ocean and stimulating biological productivity. Let's take a quiet moment to think about the nitrogen cycle. Nitrogen makes up about 78% of the atmosphere, the most abundant gas. By far, it is essential for life, being a component of proteins and nucleic acids. But most organisms cannot use atmospheric nitrogen directly. It must first be fixed, meaning converted into a form, like ammonia or nitrate, that living things can use. Nitrogen fixation is done by certain bacteria and archaea, including cyanobacteria in the ocean and root nodule bacteria in the soil. Lightning also fixes small amounts of nitrogen during ice ages. With drier, less vegetated soils and different ocean circulation patterns, the nitrogen cycle would have been somewhat different. Ice cores show changes in nitrogen-related compounds that track the glacial cycles. Nitrogen, mostly invisible and inert, flowing through all living things and returning to the sky, is another of the slow, quiet processes that underlie the Ice Age world. Oxygen, the second most abundant gas in the atmosphere, has also varied over geological time. During the Carboniferous period, about 300 million years ago, atmospheric oxygen was as high as 35%, compared to today's 21%. This high oxygen level supported enormous insects, including dragonflies, with wingspans over 60 centimeters. The high oxygen also made wildfires more common and intense during glacial periods. In more recent Earth history, the changes in oxygen are much smaller, a few tenths of a percent, driven by changes in photosynthesis and organic carbon burial. The oxygen cycle is intimately tied to the carbon cycle. Every molecule of CO2 absorbed by photosynthesis produces a molecule of O2. The ice ages don't dramatically change oxygen levels, but they do alter the balance of the carbon and oxygen cycles in subtle ways that are recorded in the chemical signatures of ancient rocks and sediments. Plankton are responsible for about half of all the photosynthesis on Earth. These microscopic organisms, mostly single-celled algae and cyanobacteria, drift through the surface waters of the ocean, absorbing CO2 and producing oxygen. They form the base of the marine food web. Phytoplankton blooms can be so large that they are visible from space, turning the ocean surface various shades of green and blue. During ice ages, the distribution and productivity of phytoplankton changed with the changing ocean temperatures, circulation patterns, and nutrient availability. More iron deposition during dusty glacial periods may have stimulated productivity. In some regions, changes in phytoplankton productivity affect how much CO2 is drawn out of the atmosphere and transferred to the deep ocean, the biological pump, the vast, invisible ocean of tiny plants floating at the surface of the sea, quietly processing the planet's carbon, gently moving forward toward the very end of our long, quiet journey. The sulfur cycle intersects with ice age dynamics in an interesting way. Volcanic eruptions release sulfur dioxide into the atmosphere, where it reacts with water vapor to form sulfuric acid aerosols. These aerosols scatter sunlight and cause short-term cooling, the kind of cooling that follows large volcanic eruptions. But on longer timescales, there is another source of atmospheric sulfur, relevant to ice ages: dimethyl sulfide, or DMS, produced by marine phytoplankton. DMS escapes into the atmosphere and oxidizes to form sulfate aerosols, which act as cloud condensation nuclei, tiny particles on which water vapor condenses to form clouds. More clouds over the ocean reflect more sunlight, causing cooling. This link between ocean biology, sulfur, clouds, and temperature, called the claw hypothesis, is an intriguing, if still uncertain, piece of the Ice Age climate puzzle. Life itself may participate in modulating the climate. Ice Age cycles have even influenced the evolution of human cognitive abilities. According to some hypotheses, the variability selection hypothesis, proposed by anthropologist Richard Potts, suggests that the highly variable climate of the Pleistocene, the alternating glacials and interglacials, the droughts and floods and shifts in vegetation, favored the development of behavioral flexibility, complex problem solving, and social learning in human ancestors. Rather than specializing for a particular environment, our lineage became generalists, capable of adapting to widely different conditions. The large brain, the language, the culture, the technology, perhaps all of these, at least in part, are responses to living through millions of years of climate variability. We may be, in the most literal sense, children of the Ice Age, shaped by the same rhythmic cooling and warming that carved the valleys and scattered the boulders across the glaciated landscapes of the North. And we can take a moment to notice how peaceful everything is. The ice sheets that still exist today in Greenland and Antarctica are not just remnants of the last ice age. They are active participants in the current climate system. They reflect sunlight, cool the surrounding air and ocean, drive atmospheric circulation, and lock away vast quantities of fresh water. The flow of cold air off the ice sheets drives persistent wind patterns that affect weather across large regions. Antarctica's ice sheet is so high, the average elevation is about 2,300 meters, that it creates its own weather, with the cold, dense air constantly draining off the plateau in katabatic winds that can reach hurricane force. Near the coast, the ice sheets are not passive features of the landscape. They are dynamic, active participants in the climate, influencing conditions far beyond their own edges. The Antarctic bottom water is one of the coldest, densest water masses on Earth. It forms when extremely cold air, blowing off the Antarctic ice sheet, freezes sea ice around the continent. As the sea ice forms, it expels salt into the water below, making it very dense. This dense, cold, salty water sinks to the very bottom of the ocean and spreads northward across all three ocean basins, Atlantic, Pacific, and Indian. It is one of the deepest and coldest water masses in the ocean, and it ventilates the abyssal depths of the ocean, carrying dissolved oxygen to the deep sea. Antarctic bottom water formation is sensitive to changes in temperature and the amount of sea ice around Antarctica, and it played a role in Ice Age carbon dynamics by affecting how much CO2 the deep ocean could absorb and hold. The very bottom of the ocean, kilometers below the surface, utterly dark and still, is filled with water that started its journey at the surface of the Southern Ocean, near the Antarctic ice. The concept of hysteresis in climate science refers to the fact that the climate system may follow a different path as it warms than it did as it cooled. Some climate states are self-reinforcing. Once you're in them, they are difficult to leave. The deep glacial state, with its vast ice sheets and low CO2, may require a larger push to melt out of than the same push that would have prevented the glaciation from beginning. This asymmetry, the different behavior of the climate system on the way in versus the way out of a glacial period, helps explain why ice ages build slowly but tend to end more quickly. The climate has a kind of memory, a reluctance to change that makes transitions in one direction harder than the other. It is not inertia exactly, but something like it, a preference for staying in whichever state it currently occupies. Now, as we continue, let's settle more deeply into the soft, quiet story. The Black Sea has an interesting deglaciation story. During the glacial maximum, sea levels were low, and the Black Sea was an isolated freshwater lake, much smaller than today, around 8,400 years ago. As the Mediterranean Sea rose with global sea levels, salt water from the Mediterranean may have breached the Bosphorus sill, the natural barrier at what is now Istanbul, and poured into the Black Sea basin. If this happened, the flooding would have been dramatic, a great inrush of salt water into the freshwater lake, raising the Black Sea level and transforming its ecosystem. Some researchers have proposed this event as the basis for ancient flood myths, including the story of Noah. The hypothesis is debated, and the details are still being worked out, but the basic idea that the end of the Ice Age brought real, dramatic changes to coastlines and water bodies is well established, gently moving forward toward what comes after the ice. As ice sheets melted and retreated, they left behind a landscape that was initially barren. Scraped rock, bare sediment, cold meltwater lakes. But life moved in quickly. Geologically speaking, mosses and lichens established themselves first, breaking down the rock and beginning to build soil. Then grasses and sedges, then dwarf willows and birches in sheltered spots, then gradually taller shrubs, and eventually forests. As the soil deepened and the climate warmed, this ecological succession, the progressive development of ecosystems in newly deglaciated terrain, can still be observed today. In places where glaciers are retreating, the foreland of a retreating glacier, exposed over decades, shows this succession compressed in space. Bare rock near the current glacier terminus, then moss and lichen, then grasses, then shrubs, then small trees, a miniature version of what happened across entire continents over thousands of years. Reindeer, caribou in North America, are one of the most Ice Age adapted large mammals. Still alive today, they have wide, flattened hooves that act like snowshoes, allowing them to walk on soft snow. Their hooves also have a sharp edge for digging through snow to reach the lichen below. Their coats are extraordinarily insulating. Each hair is hollow, trapping air for insulation, and the dense underfur provides additional warmth. Their noses pre-warm cold air before it reaches the lungs. They are the only deer species in which both sexes have antlers. Reindeer are highly migratory, traveling enormous distances between summer and winter ranges, following the edge of the productive tundra as it shifts with the seasons. They are, in many ways, perfectly tuned to the cold, shifting landscape left by the retreating ice. Living examples of Ice Age adaptation that persist into our warmer world. And we can take a moment to notice the long arc of time, based on Milankovitch cycles alone. Without human influence, the next glacial period would likely begin in about 50,000 years. The orbital configuration is currently moving slowly, away from conditions favorable for glaciation. The obliquity is near a midpoint in its cycle, and heading toward values that favor more moderate seasons. The combination of orbital factors that drive glaciation won't align again for a very long time. However, human activities have significantly increased atmospheric CO2 from pre-industrial levels of about 280 parts per million to over 420 parts per million today. This elevated CO2 may delay the onset of the next glaciation for hundreds of thousands of years, or prevent it entirely within the current orbital regime. In altering the carbon cycle, human civilization may have inadvertently extended the current interglacial far beyond its natural duration. The relationship between CO2 levels and Ice Age onset has been modeled in various ways. Some research suggests that for a glaciation to begin, under the current orbital configuration, CO2 would need to drop to around 240 parts per million, or below, well below today's levels, given that human emissions have pushed CO2 to 420 parts per million, and rising. The conditions for the next glaciation have been effectively forestalled for the foreseeable future. This is a profound thought, that human activities, which have accelerated in the span of just a few centuries, have altered a geological process that operates on 100,000-year timescales. The next ice age, which would have begun in a quiet, inevitable way 50,000 years from now, may now never come, at least not in the way the Milankovitch cycles alone would have delivered it. The study of ice ages also transformed our understanding of geological time. Before the recognition of ice ages, most people, including most scientists, had no framework for thinking about millions of years of Earth history. The discovery that ice sheets had repeatedly advanced and retreated over the continents required thinking about time on a scale that was essentially unprecedented. In human experience, it opened the door to understanding that the Earth was not a static backdrop for human history, but a dynamic system that had been changing, slowly and dramatically, long before the first humans walked its surface. The ice ages were, in a sense, the entry point through which modern humans first grasped deep time. The vast, incomprehensible duration of Earth's history, stretching back billions of years before any of us were here. There is something deeply calming about thinking about geological time, the problems and concerns of daily life, seen against the backdrop of 4.5 billion years of Earth history, acquire a different proportion. The ice sheets that covered North America were built up, grain by grain, snowflake by snowflake, over tens of thousands of years. They melted, just as slowly. The land rose after them, and is still rising. The forests returned. Life adapted, evolved, diversified. The world, in the end, is extraordinarily patient. It has survived mass extinctions, snowball glaciations, supervolcano eruptions, and the slow drift of continents. It will continue, long after the present moment has become geological history. In the vast sweep of time, this night, this breath, this quiet thought, drifting gently through your mind, is a very small and very peaceful thing. Scientists who study past climates, paleoclimatologists, often speak of their work with a kind of quiet reverence. There is something extraordinary about holding a piece of ice that is 800,000 years old, or examining a sediment layer that was deposited during the height of the last glacial maximum. These materials are archives of a world that no longer exists. A colder, drier, dustier, icier world that was home to mammoths and Neanderthals and the earliest anatomically modern humans. Outside of Africa, the past climate is not just an academic curiosity. It is a record of how the Earth behaves, a test of our understanding of the climate system, and a guide to how the planet might respond to future changes. The past is the key to the present, and the present may be the key to the future. The ice remembers, and in reading its memory, we begin to understand our own. The Vostok ice core, drilled at a Russian research station in Antarctica in the 1990s, was one of the most transformative datasets in the history of climate science. It extended the ice record back 420,000 years, covering for complete glacial interglacial cycles, when the CO2, methane, temperature, and dust records from the core were plotted together. The result was remarkable. All four variables tracked the same rhythm, rising and falling together across 4 ice age cycles with extraordinary regularity. The Milankovitch cycles were written clearly in the ice. The CO2 and temperature records were particularly striking in their tight correspondence. For many scientists, the Vostok data was the moment when the ice age theory went from well-supported hypothesis to near certainty, the ice had spoken, clearly and unmistakably, across 420,000 years of quiet accumulation. Antarctic ice cores have since been extended even further to 800,000 years at the Epica Dome sea site. Plans are underway for even deeper cores that could potentially extend the record back 1.5 million years, past the mid-Pleistocene transition we discussed earlier, into the time when glacial cycles were shorter and ice sheets smaller. These deep ice cores would provide direct evidence about atmospheric composition during the older 41,000-year glacial cycles, helping scientists understand why the transition to the longer 100,000-year cycles occurred. The drilling is slow, careful, painstaking work, conducted in one of the harshest environments on Earth, at altitudes over 3,000 meters, in temperatures that can drop to -80 degrees Celsius. The scientists who do this work have a particular patience that seems fitting for the timescales they study. The quiet wisdom of the Ice Age story is perhaps this: that change is always happening, even when it cannot be seen. The Earth is always moving, in its orbit, in its tilt, in the slow drift of its plates. The atmosphere is always adjusting, absorbing and releasing carbon, responding to temperature, moving moisture around the globe. The ice is always responding, building during cool summers, melting during warm ones, advancing in millennia of cold, retreating in millennia of warmth. Nothing is fixed, nothing is permanent. The land we stand on was buried under kilometers of ice. Not so long ago, the seas we sail were once dry land. The forests that shade us retreated to tiny refugia during the last glacial maximum. And all of this happened without urgency, without drama, simply through the patient, steady operation of the laws of physics, chemistry, and orbital mechanics. The world changes, gently and inevitably. Over time, there is a concept in ecology called the slow variable, a process that changes so gradually that it is invisible on human timescales, but that ultimately determines the state of the system. Ice sheets are slow variables, so are deep ocean temperatures, soil carbon stocks, and forest cover. These slow variables set the boundaries within which the faster variables, weather, seasons, species populations, operate. When slow variables cross a threshold, the whole system can shift into a new state, which itself persists for a long time. Ice ages are, in a sense, the story of slow variables, the patient accumulation of ice, the gradual cooling of the ocean, the slow drawdown of atmospheric CO2, crossing thresholds and creating a new world. And then, the slow variables shift again, and the world, just as patiently, thaws and greens and warms once more. The word glacial, in everyday language, means very, very slow, as in, the project is moving at a glacial pace. This is a nice example of scientific terminology seeping into common usage, carrying with it the meaning earned by years of scientific observation. Glaciers do move slowly, a few centimeters to a few meters per day, in most cases, but over centuries and millennia, this slow movement accomplishes extraordinary things, carving fjords, grinding mountains to powder, depositing drumlins and moraines across entire regions. The lesson of glaciers, perhaps, is that patience and persistence can accomplish things that seem impossible. In the short term, the ice doesn't hurry. It simply keeps moving, keeps accumulating, keeps grinding, and in doing so, it reshapes the world. Every ice age that has ended has eventually been followed by another. The rhythm of the Milankovitch cycles continues, regardless of what happens. At the surface, the orbital mechanics are not affected by anything that life or civilization does. The Earth will continue to wobble and tilt and stretch its orbit on its ancient timescales. The question of when and whether the next glaciation will begin is partly a question of what the natural orbital forcing will be in the distant future, and partly a question of what the atmospheric CO2 concentration will be at that time. But on the longest timescales, millions and tens of millions of years from now, the continents will have moved to new positions, the solar output will have changed, and the climate will be governed by conditions we cannot predict. In detail, the ice ages we have been discussing tonight are part of one particular icehouse era, one chapter in a story that stretches back billions of years and forward into a future we can only dimly imagine. And perhaps the most quietly wonderful thing of all is this: all of these processes, the orbital cycles, the ice sheets, the ocean currents, the carbon cycle, the evolution of life, are not separate, independent things. They are aspects of a single, integrated system. The Earth is not a collection of parts. It is a whole, a planet in which rock, ice, ocean, atmosphere, and life have co-evolved over billions of years, each shaping and being shaped by the others. The ice ages are not something that happened to the Earth. They're something the Earth does, a natural rhythm of the living planet, as fundamental as the seasons, just played out on a timescale far longer than any human life. In breathing slowly, in and out, in cooling and warming, in building ice and melting it, the Earth is doing what it has always done, being fully, quietly, patiently, itself. And so, we have come very gently to the end of our journey tonight, through the orbital mechanics of a spinning planet, through the slow spread of ice across the northern continents, through the memory held in glaciers and ocean sediments and cave formations and pollen grains, through the lives of woolly mammoths and early humans crossing a land bridge that no longer exists, through the chemistry of CO2 and the physics of light and the patient grinding of rock into dust. We have traveled very far tonight, across an enormous span of time, and yet we have done it very quietly, very slowly, without rushing. There is no need to rush. The ice ages are still with us, in a way, in the ice that remains at the poles, in the slowly rising bedrock of Scandinavia, in the U-shaped valleys and the fjords and the drumlins, in our own DNA, shaped by millions of years of living through cold, variable climates. And now, as we rest here together, the Earth is continuing to move, very slowly, through its orbit, tilting very gently on its axis, the ice at the poles, sitting quietly under the dark sky. The world is doing what it has always done, being patient, being slow, being itself, and you can let all of that go now. You don't need to hold on to any of it. The ice ages happened without any of us, and they will continue without any of us, and that is a very peaceful thing to know. The world is old, and it is patient, and it will carry on, slowly, gently, and you can simply rest. If this video helped you relax or drift towards sleep, a quiet like and subscribe would mean a great deal. It helps more people find their way here, to this calm and quiet place. Thank you for being here tonight. Good night. And so, we have come very gently to the end of our journey tonight, through the orbital mechanics of a spinning planet, through the slow spread of ice,